Hello, everyone. Welcome to our seminar series on games, decisions, and networks. Today, our speaker is Professor Saurabh Amin. He is an associate professor in the Department of Civil and Environmental Engineering and a member of the Laboratory for Information and Decision Systems and the Operations Research Center at MIT. He received his PhD in Systems Engineering from the University of California, Berkeley in 2011. His research focuses on the design and control of infrastructure systems using game theory and optimization in networks. His work spans three main areas: resilient network control, information systems and incentive design, and optimal resource allocation in large-scale infrastructure systems. Thank you very much, Saurabh. We are delighted to host your talk, and you can start.
Thank you, Mohammed, and thank you to the co-organizers also for inviting me. And it's a pleasure and honor to give this talk in this seminar series. So this is joint work with Mansi Wu, who graduated from MIT and currently is a Simon Scholar at UC Berkeley and also a postdoc. And she'll be joining Cornell University next year. And of course, Asos Dagler, whom many of you heard, I think, 2 weeks ago. Okay. So in our work, we are motivated by the prevalence of ML or AI-driven platforms who actually provide a variety of services, information services, and other mobility services to a large number of travelers. And our work, broadly speaking, is actually motivated by the following questions. How do the platforms provide information to a large number of users? How do actually users make decisions in using this information and utilize that network? And how do the resulting network condition after the users have made their decisions really give feedback to the platform so that they can actually come up with a new estimate of the network condition? So in this particular talk, we'll be focusing on a game theoretic foundation to model strategic behavior of users with less than perfect information about the uncertain state in the network, which may arise because of incidents, accidents, weather events, or other capacity reducing events. And we'll try to see how this game theoretic foundation has some implications for the design of information and incentive mechanisms to reduce various inefficiencies, in particular congestion inefficiency, and improve social welfare. Okay. So to motivate, I'm going to give two examples, and both of them must be maybe familiar to you or maybe not. The first one is the fact that despite the prevalence of information systems, their effect on the overall transportation system is not always positive. And this is actually, for example, there has been reports of Waze and other navigation apps creating congestion on local neighborhoods, but also the effect of information on the users themselves who use this information may not be something which is positive. And so what we need is a modeling approach to understand how the information impacts users' decisions and how those decisions result in the overall network congestion. The other example which I will give is the re-equilibriation of traffic after a prolonged and sudden network disruption. And a very sort of well-known example is this collapse of a bridge over the river Mississippi in Minneapolis. And what happened was, after this event, the surrounding detectors actually witnessed increased flow fluctuation for several weeks after this event relative to, for example, a previous week or previous year. And this indicates that the travelers are responding to the network disruptions and they are trying to gather information and trying to learn about the underlying latent state of the network. And essentially, the learning foundation of this particular type of systems is actually not very well understood. And so what we'll be also focusing on is a learning foundation where the travelers are able to learn through the information that they are being provided while adjusting their strategies in a dynamical manner. Okay, so this is the broad two motivations, which leads to the two parts of the talk. In the first part, I'm going to focus on a value of information systems in routing games. And in the second part, I'm going to focus on a learning dynamics, which actually accounts for the role of information platform as an aggregator and analyze how the agents may be adaptively updating their strategies. Okay. So let's move on to the first example. And if anybody wants to interrupt me in between, please unmute yourself or ask Mohammed to answer, to sort of prompt me and ask questions. So I'm very happy to answer in between. Okay, so let's try to sort of dwell into the part one. And this is essentially a setup where what you have is an uncertain network state, which may be affecting a number of links in the network. This may be actually correlated events. And there are multiple information service providers in this setup, for example, Google, Waze, and Apple Maps. And the key point that I want to stress here is that there are inherent heterogeneities, both in the access and the accuracy of the information which is provided by the systems, because they may be different in terms of how they are utilized by the systems or what is the underlying technological means through which they are generating this information. So the empirical evidence indeed suggests that there is heterogeneities because, in this particular example, which you see here, there are differences in the realized travel times in trips of using various apps from Mountain View to the San Francisco Bay Airport, and which indicates that if there are different travel times, this may actually ultimately also impact how the travelers are going to use these apps. And in effect, their usage of these apps or market shares of these apps are going to influence the way in which the information is distributed among heterogeneous set of travelers. So there are two questions that we'll seek to focus on. One is how heterogeneous information influence travelers' choices, and how can we assess this quantity that I will define, the relative value of information, and try to have some guidance about the adoption rates of various information systems. So before I go on, I just want to briefly comment on the related work. And of course, our work is built on rich literature in congestion games and value of information in game theoretic settings. But more particularly in the context of transportation, our work extends some of the insights which were obtained by people in transportation community who considered simpler information environments or simpler network structures. The work is also complementary to a very nice paper by Daron, Asu, Ali Makhtoumi, and Azharaksh Malekian, who actually studied informational brace paradox, which is trying to understand how information and the network structure can be studied together. And the kind of work that we will be presenting is going to be a Bayesian approach, which is complementary to what their approach is. The overall approach that I will present here can also be applied to departure time choice models. For example, Vickery's bottleneck departure time choice model. And in another paper, we have extended the similar kind of results, for this departure time choice models. Okay. So before I move on, I will try to give you a simple example to illustrate the main insights. Okay, so this is a simple two-route example, and everything which we will study in this context is going to be obtained from this simple example. So there are two routes, and the main route is the highway, which is actually an uncertain, faces an uncertain state, let's say incident or no incident. And the detour route is having no incident. And the time cost, for the sake of simplicity, are linear in the flow, and the highway under the incident actually faces higher cost relative to the highway under no incident state. And the asymmetric information structure is also simple to begin with. So there is two populations. A fraction of travelers are having access to complete information about the accident or incident state. And the other population, which is population 2, have no information about the incident. So they are having 0.5 probability on both states. So what happens in an equilibrium for this simple game? So there are two cases of interest. And the first case is when the size of the informed population is relatively small. So in this case, what happens is that the informed population is able to take solely the route based on its state, which means that if there is no incident, all the informed populations are going to take the highway. And if there is incident, they are going to avoid the incident by taking the detour. Now, since the uninformed populations are relatively large and they do not have any information about the state, they necessarily have to split between both routes. Okay, so that is one behavior that arises. The second type of behavior that arises in this context is when the informed population size is large. Okay, so now what happens is that they were taking detour before, but now their size is so large that they cannot afford to take only the detour road only, and they necessarily have to split their routes on split their flows on both routes. And the uninformed population also splits their flow in both routes in this case. Okay, so this is actually the two types of qualitatively different behavior that arises in this game. Now, what about the equilibrium costs of individual travelers in each of these populations? So what we see here is that when you have the informed population relatively small in equilibrium, the informed population actually faces lower expected cost in comparison to the uninformed population. However, after this particular threshold, the informational advantage completely disappears and travelers in both populations face identical cost in equilibrium. Okay. Alternatively, we are going to consider this quantity, which we call as the relative value of information, which is simply the difference between the two costs in equilibrium. And essentially, this is a measure of the gain in the cost, in the travel time savings, an uninformed traveler is going to get if it were to have access to more information or complete information in this case. So again, here when the lambda is smaller than this threshold, the relative value of information is positive. And when it is above this threshold, it is 0. Okay, so it vanishes. The value of information vanishes above this threshold. Even more interesting behavior appears when you have a situation where, as before, there are two populations, but they're both informed. Now, the first population is relatively more accurately informed in comparison to the second population, who is relatively less accurately informed. And in this case, there is an appearance of a second threshold, okay, where the second population is relatively small in size. And in fact, it actually starts to experience lower congestion cost in comparison to the more informed population. So in this particular regime, the better informed population face a higher congestion, higher cost, because the congestion externality starts to dominate the value of information which is getting because of the more accurate information access that they have. So what we are going to see, and this is the insight that prevails in a much more general environment, that there are two thresholds here. And in the two side regimes, which is this one and this one of the populations is minor, and the minor population actually faces lower expected costs. Okay, so the information is beneficial to the minor population. Whereas in the middle regime here, what we have is neither population is having an informational advantage. And in particular, both populations will face the same expected cost in equilibrium. And the induced route flows and the costs are not going to change with perturbations in the population sizes. Okay. So this is actually the main kind of insight that I wanted to first start with. Okay. So now in the next few slides, I'm going to present a general model, and then I'm going to tell you a way which we have developed to analyze this in that more general context. So what we have is Bayesian congestion game. So there is a general network which with single origin, single destination pair, and there's a finite set of states that can be realized, and they are realized according to a prior theta. The edge costs are state dependent, and they are, for simplicity, increasing as a function of the load in that edge. Okay, and we are going to consider non-atomic demand, inelastic non-atomic demand. All right. So there are multiple heterogeneous information systems, and as I mentioned before, they differ in their access and accuracy level. Okay. So the access or the subscription of information system I creates a population I, and their size is lambda I. The size of the population which is subscribed to information system I is lambda I. And the key quantity of interest is this population size parameter, which is the subscription sizes of different populations to different information systems. Now, in the context of Bayesian games, what we have is each information system sends a noisy signal to its subscribers, which actually is its private information. And for the sake of simplicity, we are going to assume a common prior setting, which means that the joint distribution of the state and the types received by all the populations is common knowledge. What I'm going to tell you is under this common prior assumptions, but the general insights also actually hold for subjective beliefs, which we have analyzed separately. It's just that the mathematics is not so nice in the case of subjective beliefs when common prior assumptions does not hold. Now, I want to emphasize that the key advantage of this Bayesian approach is that we can model fairly general heterogeneous information environments, in the sense that signals can be correlated or independent, and we do not assume any particular ordering in terms of the accuracy of the signals. In particular, one information system may be more accurate in one state but less accurate in another state, for example. Okay. So the travelers in population I choose their routes based on their private signal, and their strategy is a mapping from their private signal to how their demand is routed over the network. The induced route flows and the edge loads can be computed simply as a linear functions of the strategies. And finally, we have the edge costs, which are state dependent as a function of the realized edge loads. All right. Yes, Ozan?
Clarification question. So is the state binary?
No.
Arbitrary?
So it's a finite number of states. So it is not binary, finite, and the state can actually affect one of the state can affect edges, the cost of multiple edges at the same time. So it doesn't have to be associated with capacity reduction or cost increase in one of the edge.
Okay, and I guess you're also assuming that the users cannot multi-home, like I cannot get signals from multiple information sources. I can't.
So I can actually have two apps in front of me, or I can, but ultimately I will actually ignore one and select one, right? So choose to follow the one which I'm using to sort of route my decision. So that is the kind of thinking.
Okay, so I see. But
we do not explicitly model this kind of thing where the users are simultaneously looking and trying to decide. No.
Okay, but is that the users decide which app to subscribe in your example?
So the kind of insights that we are going to get is that we obtain general insights for this population size distribution, and then based on how you want to interpret it, it could be any of the interpretations. Right. Yeah, but the main results is actually for the population size vector, right? So there is no sort of particular thing that this user actually is going to choose this app. It's just the size of the populations that's going to matter.
Right. I mean, the reason I was asking is that I was thinking that if we actually have a first stage where users decide on which app to follow.
I will put that extension once I get through the story. Yes, so that extension is rather straightforward. Yeah.
Thank you.
Good, wonderful. So what we have is each traveler population has a type which actually calculates its private belief based on a posterior update on the common prior. And based on this private belief, there is going to be an expected cost of a particular route. Okay. So a Bayesian wardrobe equilibrium is a straightforward extension of a wardrobe equilibrium where each population type chooses its route based on the lowest expected cost based on its private belief. Okay. Now, I'm not going to go to the details of this. You can actually map this into the classical terminology of a Bayesian game and define an ex-ante, interim, and ex-post stage. But the key quantity here is, again, the population size vector and this notation gamma, which is I'm going to use for denoting this particular Bayesian routing game. Okay, so now, remember in our two route example, there was a trade-off between the gain of information and the congestion externality, which is imposed by the others in the same with same information. And we had these three regimes with positive, zero, and negative value of information. And we had this quantity called relative value of information. So now in the next couple of slides, I'm going to tell you about our approach, which actually extends this same insights to a general network with multiple states, information systems, and signal distributions. Okay, so let's get on with this plan. So the first thing which actually relates our routing game with the potential games is that our game is a weighted potential game with a similar potential function, but there is this common prior here. And the weight corresponds to the marginal probability of a particular type. So that is the weighted potential game sort of insight. And using this insight, what we can argue is that a strategy profile is a Bayesian wardrobe equilibrium, if and only if it is a solution of this convex optimization problem, where you minimize this weighted potential function subject to feasibility constraints. Now, because of the common prior environment, and because of the fact that the cost functions are increasing in the edge load, we also have essential uniqueness of our Bayesian wardrobe equilibrium. Now, it turns out that it is much easier to operate in terms of route flows instead of the strategies, the strategy profiles. So what we are going to do is that we are going to study how the set of route flows, in particular equilibrium route flows, are going to change as a function of lambda, as lambda changes. Okay. Now, in order to sort of characterize the set of feasible route flows, there is a very interesting and important quantity that arises, which is the impact of information on a particular population. So intuitively, it is the maximum amount of change in the routing behavior a particular population is going to experience when it receives one type over the other. Okay. So that is the impact of information metric that we define. And intuitively again, this impact of information should be no bigger than the population size, the total population size itself, okay? So this is an important set of constraints that arise. And this set of constraints, in addition to other very natural constraints such as type independence, non-negativity and demand balance, which I'm not going to detail because that's not that important, define the set of feasible flows, okay? Now note that the only set of constraints where the size arises is the information impact constraints, and this does not appear in any other constraints, okay? So equivalent to the characterization of the strategies, what we have is a feasible route flow is an equilibrium route flow if and only if it minimizes the weighted potential function subject to these constraints. And remember that the information impact constraints are the only constraints which has the lambda parameter in it. So essentially, we can try to sort of study the sensitivity of the equilibrium route flows with regard to perturbations in population sizes by trying to evaluate the tightness versus not of information impact constraints. So by studying the tightness of information impact constraints, we can try to characterize the equilibrium structure. Okay, is this clear? Okay. So similar to this two population example, what we have is that if we have any two population, let's say I and J, and keep the sizes of all other populations as fixed, what we have is these three different regimes based on the tightness of the information impact constraints for that population, okay? So in the leftmost regime, you have the population I being small relative to that threshold, relative to a certain threshold, and the information impact constraint for that population is tight in equilibrium. So the impact of information is fully attained in some sense. And analogously for the other extreme, where the other population is having its information impact constraint being tight. And these two thresholds actually depend on the beliefs and the sizes of the populations and can be computed as linear programming solutions. And lastly, in the middle regime, none of the populations are minor, so the information impact constraints can be dropped because they are not tight. And essentially, the equilibrium outcome is independent in this middle regime with the perturbations of the population sizes between I and J. Okay. And we can actually try to sort of precisely characterize this relative value of information, which we defined as Cj star minus Ci star. Remember, it was defined as the marginal gain that a traveler is going to get if it were to shift from population J to population I. And this is in fact negative of the directional derivative of the potential function in equilibrium, of the value of the potential function in the equilibrium. Okay? So this directional derivative is in the direction in which the perturbation is happening between population I and J. So in fact, this particular directional derivative is monotonically decreasing. So we get the relative value of information as decreasing as the population's I size increases. It is 0 in the middle regime, and then it increases again. Okay. All right. So this is just a summary of what we just said, that one population has an advantage over other population if and only if its size is below a particular specific threshold. And the key point I want to sort of convey again for the last time is that the key aspect is the congestion externality that starts to increase as the population I size starts to increase in moving from left to right. And this directly provides us the non-increasing nature of the relative value of information between population I and population J, which means as population's I size increases and population J size decreases. Okay, so this is a full characterization of relative value of information between any two arbitrary pairs of populations given their size perturbations. All right. So now let us go back to the question that Uzan asked. So how can we use this kind of characterization for a more general sort of game, let's say a two-stage game, where in the first stage, as he mentioned, the travelers can choose their subscription levels. And in the second stage, they play a Bayesian routing game given their subscriptions. So what will be the equilibrium subscription levels? So what are the set of equilibrium subscription levels in such a game? And so what we can argue based on our relative value of information insight is that in such a game, a population, if an information system I is chosen with a non-zero subscription rate, then it must provide you the smallest expected cost or the lowest expected cost in equilibrium. Okay, and if you have such a realization of your sort of subscription vector, this will be a possible equilibrium market share. And in fact, we can show that this can be characterized as a set of a non-empty convex set, which basically minimizes this value function in equilibrium. Okay, so any such minimizer is a plausible equilibrium market share. And in this case, the equilibrium edge load is again size independent, that we can also show, which means that the equilibrium load is not going to change with regard to the perturbations in the sizes of the populations. Okay, so this is one of the applications of the relative value of information characterization that we study. Okay, so there is another application of this characterization, which actually points to a very emerging sort of set of ideas in information design. So in our case, what we have is a simple example where we are motivated by the desire of introducing or limiting the flows of traffic in a certain alternative route. And in this case, using the same framework, what we can do is that we can design an information mechanism, a Bayesian persuasion mechanism, where the travelers may have choice of information system, so whether they want to subscribe to the information or not. And in that sense, the information environment is endogenous. And what we can show here in using the similar ideas is that we can design an information mechanism which actually limits or which minimizes the overload on the alternative route. And of course, in such a mechanism, all travelers will also face an identical cost. Okay, so various extensions of this particular idea in the context of information design, and we can perhaps talk about it afterwards if you are interested. All right. So if there are questions about this, we can discuss now, or otherwise I can move on. Okay. Good. All right. So in the second part of my discussion with you, I'm going to focus on a more dynamic situation where there are two sort of extensions. One is that the information platform is actually providing or enabling learning by these strategic travelers about the underlying latent state. And the second is that the realizations from the outcomes of the game is going to be used by the information platforms to update the information and provide an updated information in the next step. So in this particular dynamics, the players repeatedly interact with each other in an unknown environment, and the public information system is mediating or is enabling this learning and adjustment behavior on the part of these strategic agents. Okay. So in the context of transportation, recall this collapse of I-35 bridge. And so there we saw that the travelers were adapting their routing decisions while learning an underlying uncertain state. So the uncertain state again represents the latent network condition, and the realized travel times are based on this random and state dependent costs. Okay, so there is a feedback loop between the public information system and the travelers, because the travelers use the updated estimates from the public information system, and the public information system utilizes the realizations of flows and travel times on the utilized edges to update their estimates. Okay. So this is a much more general sort of story. This could be extended to other types of games as well. So where on one hand you have players which are strategically interacting with each other in a game with an unknown payoff relevant parameter. And on the other hand, what you have is an information platform, which is an aggregator of information, which accrues or which obtains data from realized outcomes and sends an updated imperfect state information or a parameter estimate for the travelers to learn and adapt their strategies. So then the question is, how do the strategic players repeatedly adjust their strategies while learning via this platform? Okay. Now, I want to mention that this particular learning dynamics has several characteristics which actually relate to classical results in best response and fictitious play under complete information environments, as well as an extensive amount of work, including in potential games on distributed learning in games. Okay. So the key sort of feature of our stochastic dynamics or learning dynamics here is that it is a combination of learning of an unknown parameter, okay, as well as learning in games under this imperfect information about the underlying unknown parameter. And there's a feedback, as I mentioned. So this dynamic interplay, again, is actually something that requires new tools and new analysis based on the existing ideas, because of the reason that the platform aggregates information and has access to the realized data, which is non-IID, because of the endogeneity of the data generating process, because this is being generated by the players' strategic actions. And then the players, of course, are choosing their strategies based on the imperfect information which is provided by the platform. Okay. So this non-endogenate, this endogeneity of the data generating process and the non-IID nature of the data requires us to sort of develop new tools, or at least combine the existing tools. And so what we do in our paper is to sort of in order to handle the learning of the unknown parameter, we try to resort to results in martingale theory. And in order to handle the learning in the games part, the strategy part, we build on the results in the learning in games. And our focus in this paper is on long run outcomes. And we focus on convergence aspects, where we want to understand the properties of the outcomes in the long run, but also in contrast to a variety of work in this area, we also try to study stability properties, both local and global stabilities. And we try to also provide ways of thinking about when might complete learning happen. So when might information aggregate? And the kind of results that we develop here, I will try to apply to potential games, but they're also applicable to zero-sum and dominance solvable games and other examples where our conditions hold. So let me try to describe our model. So it's a players play a game in multiple steps. So there are finite number of players. As before, there is an unknown parameter from a finite set. And there is a true parameter, which is S star, and the players in each step choose their strategy QK. Okay. Now the players' outcomes are randomly realized according to this particular payoff distribution, which is parameterized by the state, which is conditioned on the strategies of the players. And without loss of generality, we could express this as the outcomes as something which is an average payoff function and a noise term, both of which could be state dependent, a zero mean noise term. So I will describe to you two things now. One is how the platform updates their beliefs, and the second is how the player updates their strategies. Okay. So in each step K, the platform has access to the data, which is the strategy profiles and the payoff outcomes. And the platform is going to use the payoff distributions to update the next step, the next belief in the next stage. And in our framework, we use a Bayesian update, but the kind of ideas that we have developed in terms of trying to deal with the beliefs using martingale type analysis can be also adapted to other types of update, including maximum a posteriori updates, maximum likelihood updates, or ordinary least square updates. The way in which this strategy updates is going to happen is as follows. So in step K, the players are going to receive an updated belief estimate, and the players are going to face an expected utility given this updated belief. Okay. So this is a classical best response type, best response definition, where the players, the myopic players are going to use best response to come up with their next strategy based on the updated belief and the play of the other players in the previous step. So in particular, we can consider three types of best response strategies, updates. One is the simultaneous, where everybody updates according to best response, sequential, where player takes turn, and inertial best response, where there is linear sort of weighting function of the previous strategy and the new best response strategy based on an updated belief and other players play. Okay, so which are with some learning rate alpha. Okay, so this actually creates this coupled dynamics of belief and strategy updates. Okay, so now what we are going to do is to argue for our results on convergence and stability analysis, and then I'm going to apply these results to potential games. So the first thing is that we can reasonably assume, without much trouble, that the best response should converge in in the game for a fixed theta. Because if it does not converge for a fixed theta, then it's a problem, because even in the games of complete information, the best response may not converge if this condition does not hold. Okay, so now under this assumption, the beliefs and the strategy converge to a fixed point with probability 1. Okay. And this fixed point actually satisfies two properties. One is that the belief consistently estimates the payoff distribution with the fixed point strategy, in that new information at the fixed point is not going to change the belief. Okay. And the second is that the players have no incentive to deviate from the fixed point, because the fixed point happens to be an equilibrium strategy in the game of imperfect information corresponding to the fixed point belief. Moreover, the belief converges exponentially fast. Okay. So now, just briefly as a proof idea, this actually requires a combination of, again, martingale analysis and learning in games type results. So as a first step, using classical martingale type arguments, we can show that the belief converges to sequence of belief converges to a fixed point. And since we have the best response dynamics converging with a fixed theta, although in our case, the beliefs are actually changing over time, we can fortunately show that the strategies also converge to a fixed point, even under the changing beliefs. And finally, what is going to happen is that the beliefs and the strategies are going to enter into a local neighborhood of the fixed point. And when they do that, the data generating process can be almost or approximated by an IID type process. And this actually gives us this consistency of the estimate, which means that the belief starts to consistently estimate the payoff distribution. And it also gives this result of exponential convergence. Okay. So this is just a convergence result to a fixed point. Now, there are a couple of interesting points I want to mention about fixed point properties. First is that, if and when information aggregates, which means that you have belief recovering the true parameter, true underlying parameter, and also having a complete information Nash equilibrium, those complete information equilibrium and full learning satisfies the conditions for fixed point strategies. Okay, but the converse is usually not true. Okay, in that the learning may not recover complete information about the underlying parameter, because the belief at fixed point may be having a wrong estimate of the payoff with strategies that differ from the fixed point strategies. Okay, and in some sense, this notion is actually similar, somewhat similar to, in its spirit, to the notion of self-confirming equilibrium, which has been proposed by Fudenberg and Krebs earlier, where the beliefs of opponent strategies may be wrong at unreached information sets. So there are some differences between our fixed point and our setup in more general than theirs, but the notion is actually somewhat similar. The aspect of fixed point strategy not necessarily recovering complete information equilibrium. The second is, when does learning recovers complete information equilibrium, which means that the fixed point belief is concentrated on the true parameter with probability 1. And this happens if and only if you have the true parameter being identifiable at equilibrium. Okay, which means that any other belief must contain at least one parameter which will have a different payoff distribution given the equilibrium strategy. Okay. And in this case, complete information equilibrium is globally stable, in that the convergence to complete information equilibrium happens to complete information fixed point happens with probability 1 for any arbitrary initial condition. So that's why it's called global stability. So essentially, the point that I want you to keep in mind here is that you have a globally stable equilibrium if and only if all the fixed points are complete information equilibrium. Otherwise, it's not possible to have a globally stable equilibrium. So this is a fairly restrictive sort of condition under which we can actually get global stability. And that's why we have to move to a notion which is that of a local stability notion. Okay. So this is my last sort of technical slide, and then we will apply this theory to potential games. So please bear with me for the next few minutes just to get the game intuition for local stability. So the local stability notion requires that if you are starting in a local neighborhood of a fixed point, you remain in a certain local neighborhood with sufficiently high probability. You can arbitrarily high probability. And this notion of local stability is in fact directly borrowed from the theory of stability of stochastic dynamical systems. So there is nothing new here conceptually as far as the definition of local stability is concerned. Okay? Now, in order to derive conditions for local stability, we again have to remember that there is a coupled belief and strategy dynamics. So we need to argue for local stability in both these belief and strategy dynamics. Okay. So it turns out that we have a set of sufficient conditions which actually builds on local stability of complete information games and extend this to sort of this kind of a more general environment, learning environment. So there are three conditions. So the first condition is local consistency. So essentially what local consistency means is that the belief consistently estimates the payoffs not just at the fixed point, but in the local neighborhood of the fixed point. Okay, and this is needed in order to ensure that the local perturbations of the belief remain close to the fixed point belief when the strategy changes. Okay, so this is the part of controlling the local perturbations of the belief, this local consistency requirement. Okay, it again uses some ideas from martingale crossing. And the second part, which is you need to take care of the strategies, that the sequence of strategies remain close to the local neighborhood. Okay? So this is actually given by two conditions together, which is local invariance and local hemicontinuity, upper hemicontinuity, I'm sorry. So the local invariance is an extension of local stability requirements in best response dynamics for complete information games. And in this case, in our case, what we require is an existence of a neighborhood of a fixed point that is invariant to local perturbations in strategy and belief. And again, local hemicontinuity is something which is fairly classical in these settings. So the summary is that in order to ensure local stability, we need to guarantee that the perturbations caused by the strategy updates results in beliefs that remain close, and then vice versa. Okay, so that's why we need these two sets of conditions. All right, so this was actually a somewhat heavy slide, but now let me try to sort of apply this kind of concepts to our original goal of routing games. And again, I'm trying to flash this picture where we have a feedback loop between the public information system and the routing decision. Okay, so what we can guarantee thanks to our convergence results, that the belief accurately estimates the cost on the edges that are taken in equilibrium, right? However, the learning can be incomplete in that if you have at a fixed point, a particular edge or a set of edges is not taken, then the complete learning is not guaranteed, because if the traveler or somebody had more information or information about the actual state, then they may have incentive to deviate from the fixed point. Okay, so that's why in such a situation, learning may not be accurate on the edges that are not taken at fixed point. So then this actually results in a question of when might learning be complete, right? When can you have that? And in the context of potential games, there are a bunch of conditions that we can have, and any one of these conditions will guarantee convergence to a complete information learning. So the first condition is that all states are distinguishable from the true state, and this is saying that a state actually impacts the costs of all edges in the network. So that is one condition where learning can be complete. The second condition on its own, which will guarantee complete information equilibrium, is going to be where the free flow travel times, when the loads are zero, are independent of the state. So the state does not affect the free flow travel time. So then the learning is complete. And the third is that if the travelers were to initially take all the edges or incentivized to take all the edges, then the learning is going to be complete. Why is the complete learning desirable? Well, it is desirable because at least in the series parallel routes where the Wheatstone network is not embedded, you can have that the average cost of all the travelers at fixed point may be more than the average cost of the travelers under complete information. So that's why, at least in series parallel networks, complete information learning is desirable. Okay. All right. So just a minor point, and then we will end and discuss. This particular learning dynamics and the theory or some kind of theoretical concepts that I illustrated is actually useful for the case of tolling design in a realistic situation, I would say, where the traffic authority does not know full information about the underlying latent state of the network. Okay. So in this case, what you have is that the traffic authority has access to the travel time estimates from the public information system and is able to sort of adaptively design toll prices. And the travelers in this case actually not only react to the updated estimates or the belief, but also to toll prices. Okay. So this is actually an example of an adaptive tolling strategy. So what we can have is that we can actually try to study the convergence of this couple dynamics with one more addition of a sequence of toll prices, which are actually also updated. And the way in which they are updated is that the tolling in a particular step is a combination of linear combination of toll in the previous step, toll vector in the previous step, and a toll corresponding to the current belief that the tolling authority has, right? And this particular toll would be the classical Pigovian prices or marginal cost pricing, which is classical in this kind of setting. And the routing strategy actually can be both best response or in fact can be an equilibrium sort of routing strategy. So I want to sort of mention that the kind of results that we develop for best response type updates can be extended to a 2 timescale setup where the updates in the beliefs are going to be at a slower time scale in comparison to the updates in the strategy. And in this case, what is going to happen is that the best response is going to converge to equilibrium corresponding to the current belief, okay, before the next update is going to be made on the belief. Okay, so that's why here I have written equilibrium updates in contrast to the best response. So what you can now guarantee that if the travelers were to take all edges, then learning leads to an optimal tolling mechanism and socially optimal routing with complete information in that the sequence of tolls will converge to the toll vector corresponding to the true state, true underlying latent state, and the load vector would correspond to, would converge to the socially optimal load vector for the true state, underlying state. Okay, so this completes our story for tolling mechanism. And I will now conclude, and then we can have a discussion if you want. We try to have a Bayesian equilibrium analysis to study the impact of heterogeneous information on travelers' choices and costs. And essentially, the main point I want you to remember is this trade-off between gain from information and congestion externalities. I believe this aspect of relative value of information can be extended to more interesting, more complicated problems, including, for example, the one which we had discussed, which is the equilibrium market share in a 2-stage game. And in the context of a more dynamic setting, what we tried to describe to you was a learning foundation to understand this interplay between parameter learning and learning in games. Our focus currently is on the long run properties, but other extensions, for example, finite time guarantees are actually quite desirable. And I illustrated an application to potential game because this was focused on routing applications, but there could be a variety of other applications of this kind of theory. There are 2 possible future ideas that I want to mention. One is on the dynamic information provision under state uncertainty, which is where the information design is not static, but is actually dynamic in the sense that new information is provided over time. So there is a lot of potential about this idea to extend it in a dynamical context. And the second is how can we sort of understand platform-based learning or platform-enabled learning, I should say, where learning can be faster either with way of trying to sort of nudge the travelers to sort of gain that kind of information or by other means, which the platform may so desire. With that, I would actually conclude and thank you very much for listening, and I'm very happy to take any questions that you may have.
Thank you very much, Saurabh. If you have any question, you can just raise your hand and unmute yourself to ask your question.
I can ask a question, maybe, Muhammad. Francesca here.
Hi.
So first of all, thank you so much for the great talk. I mean, this is super exciting area of research, I think. I just had a curiosity in the second part of your presentation. Like, if I understood correctly, agents here behave in a myopic way, right? Like the learning is done by the central planner, and agents behave according to a best response given the current estimate.
Yes.
So I was wondering whether you thought also or are thinking about the scenario where agents themselves are trying like to look at the future as well, and they are trying to
yeah, that's a very good question. Excellent question. So what we have done is we have tried to build on this best response type foundation of myopic players trying to adjust according to best response. You can also have, as you mentioned, a setting where there are long run players which actually account for a discounted cost. There are actually some, as you may also be aware, people who have considered this kind of learning with discounted cost utilities, but I'm not familiar of a particular result which actually considers this long-lived players who account for this discounted costs while also facing belief uncertainty, and if there are stability results for that. So it may just require a different kind of analysis to sort of handle that kind of a case. That being said, since this particular approach arose from this day-to-day learning in the context of transportation, we chose to sort of fully study the best response type dynamics under 2 time scales. But yes, I mean, what you mentioned is a worthy topic. It's not clear to me straightforwardly how one might actually derive stability properties for this kind of long-lived players with discounted costs. Yeah. I don't know if it answers your question, but
yeah, no. I mean, because we thought a little bit about this problem, like in the 2-road setting, but again, things become very complicated. So I'm not aware of anything like for the general network, which would be very interesting. That's why it's cool.
So, I mean, in potential games, as you know, Francesca, it may be possible. It's not clear to me whether if it goes beyond the setting of a potential game, how we can actually use the ideas for that developed in potential games with long-lived players to sort of show these convergence and stability results. Yeah, but as you said, I mean, even in 2-route case,
it's very complicated. That's why I was really curious to see.
No, I do not know how to generalize these ideas beyond if it is the long-lived players in beyond 2 routes.
Thank you.
So let me ask you a brief question as well, Saurabh. At the end of the first part, you talked a little bit about this information design ideas in addition to the main thing you covered. There was one thing that was a little bit unclear to me there, and this is the following. So if I have a population of agents going from I to J, thanks to negative congestion externalities, I may actually benefit from sending different signals to different agents in the same population in a way that kind of facilitates anti-coordination. Like when you pose the information design question in this setting, is this also a part of the mechanism, or are you, so what you have in mind is something where all agents see the same signal?
Right. So this is so first of all, in our case, a population is actually described by way of those population of travelers which actually choose to enroll or opt in to receive the information about the incident.
Right, but I guess
but now your question is that condition on receiving, so whether it is actually fully correlated in the sense that all the populations, so in our case everybody in that population receives the same realization. We could also have a situation, as you mentioned, that it's the same probability distribution, but everybody in that population actually will receive different realizations.
Precisely,
right?
And the benefit.
This is something which is again very interesting, and this will actually create a symmetric information environment where different agents will be differently sort of able to make an update on the underlying state based on their realized, based on the signals that they actually received, right?
Or in the same states, 2 agents who belong to the same population may observe different realizations and therefore have different beliefs about the state.
Different beliefs,
I mean, I guess the simple setting is one where, like one extreme is where all agents see the same public signal.
Right.
Second, the other extreme is, and then I think this still is suboptimal, but the other extreme is where all agents have independent roles from the same distribution.
Right. So I do not have a precise answer to the question about the design part, but as far as this value of information aspect is concerned, the results in that particular setup applies to all these settings where, you know, the condition on the state, the realizations, the signals which they actually receive are correlated or fully independent and things like that. What it means to sort of design a mechanism in itself is something that needs to be sort of understood for these two extremes that you just mentioned. Yeah, that would be something which would be very interesting.
And I guess there may even be more, because independent is one thing, but ideally would actually introduce negative correlations among the signals observed by different agents in the same population.
Yeah,
of course, there are limitations to how much negative correlation you can introduce, but that I feel like is something.
No, that's a wonderful comment. Yeah. No, I agree that it's a worthy question for further investigation. Yeah.
Thanks for an amazing talk, Saurabh.
Thank you.
We can have one more question before we end the talk. If there's no other question, I can ask one. I'm wondering, in the second part of the talk, you were talking about best response type of dynamics. Like, is there a way to generalize this one to like fictitious play type of algorithm dynamics?
So if
this straightforward generalization or?
Right. So for the step sizes, if they are constant, then I believe you obtain a classical fictitious play. I think the type of generalization which will be interesting is when perhaps different or similar to what you asked is when the players are asynchronously or sort of having different update rates.
Okay.
So we were able to sort of conduct some analysis of that with different sort of asynchronous step sizes. But in going through that route, we ended up using some ideas from stochastic approximation, which I think you're also very much familiar with. The kind of analysis that I presented actually avoids that part. And because we actually assume that the update step sizes for individual agents are symmetric across different agents, but this asynchronous step sizes is actually something which would be a good generalization as well. Yeah.
Okay. Thank you very much, Saurabh. That was a great talk.
Thank you.
Thank you. Thank you all.
Thank you. Bye.
Bye-bye.